Welcome to Gradient Daily, where we deep dive into an AI research paper every single day. Today, we are exploring an incredibly dense, rigorously reasoned, and frankly, mind-bending theoretical map. We're charting the transition from human-level artificial general intelligence, what we call AGI, all the way to artificial superintelligence, or ASI. We're not just talking about your favorite chatbots getting slightly better at writing emails. We are talking about what actually happens when the intelligence curve goes completely vertical. So, let's dive right into this visionary paper coming out of Google DeepMind. And look at this author list. It's authored by absolute heavyweights like Tim Genoane, Shane Legg, who is literally one of the co-founders of DeepMind, and Marcus Hutter, the pioneer of universal AI theory. This research tackles a massive, world-altering question: what happens to AI development in a post-AGI world? Think about it. If we achieve human-level AI, does progress just stop? Or does the AI itself completely take over the research and development process? And crucially, what are the systemic, physical, and theoretical bottlenecks that could actually halt this explosive progress?
Here is our map for today's explainer. First, we'll define our coordinates. Then, we'll establish theoretical ceilings with AIX, chart 4 distinct routes to superintelligence, map out the hazardous bottlenecks, and finally, wrap things up with a critical analysis.
Starting with Part 1, defining AGI and ASI. Let's make sure we're grounded and establish our baseline terms using the Legg-Hutter score of intelligence.
What's really fascinating here is that AGI is defined simply as median human-level performance on most cognitive tasks. We aren't talking about some kind of unified God mind here. In fact, current frontier models are already superhuman in very narrow, specific domains, right? But AGI marks the threshold of broad, general competence. It's an AI that can sit down and essentially do the cognitive labor of an average human worker across virtually any digital discipline. We're talking about everything from writing complex code to balancing a massive ledger, all the way to scheduling a sprawling, complex logistics pipeline.
And that definition brilliantly illustrates the massive, unprecedented leap to artificial superintelligence, or ASI. When we use the term ASI, we are not talking about a single smart human, or even an Einstein-level genius. No, we're talking about a system that dramatically outperforms hypothetical groups of tens of thousands of well-coordinated experts working over a decade on a single problem. Imagine the entire Manhattan Project or the Apollo program completely compressed into a single digital collective operating at blistering silicon speeds. That is the threshold for ASI, and it profoundly changes what is physically and computationally possible in our reality.
Now, to understand how we actually get there, we have to look at the fundamental advantages of digital intelligence over biological intelligence. Look closely at lossless replication. This is huge. If a human spends 20 years getting a PhD in physics, they can't just copy-paste their brain state into a million other humans. It just doesn't work that way. They have to teach them slowly through incredibly low-bandwidth language. An AI, on the other hand, can perfectly copy its source code and its entire lifetime of memory state in literal seconds. This lossless replication allows an AGI to effortlessly spawn billions of instances without the frustrating evolutionary bottleneck of human learning. Combine that with extremely high bandwidth input/output speeds and substrate independence, meaning the ability to easily migrate to faster and faster hardware, and you have an entity prime for absolutely explosive scaling. Moving to Part 2, Universal AI and AI ASI. This is where we ask, just how smart can a machine theoretically get? Central to universal AI is the concept of AIXI. AIXI is an incomputable, theoretically optimal agent. It represents the absolute mathematical limit of intelligence. It maximizes the Legg-Hutter score by perfectly solving 3 core problems. First, acting under uncertainty. It does this by maintaining a massive Bayesian mixture of all possible computable environments. Second, interactive decision-making. It solves the notorious credit assignment problem by perfectly balancing short-term and long-term rewards over an infinite horizon. And third, the exploration-exploitation trade-off. AIXI doesn't just wander around randomly like a lost Roomba. It naturally explores actions that mathematically reduce its uncertainty about the world completely without needing arbitrary novelty bonuses. It is, by definition, the perfect ideal learner.
But here's the catch. How does AIXI know what to believe before it has any data? Well, it relies on Solomonoff's universal prior. This is essentially a mathematical formalization of Occam's razor. It assigns a higher probability to simpler explanations, specifically environments and reward functions with lower Kolmogorov complexity. Now, Kolmogorov complexity simply means the length of the shortest computer program needed to describe an environment. Basically, if it takes 1,000,000 lines of code to explain your universe, it's significantly less likely than the universe that takes only 10 lines. AIXI uses this mathematical Occam's razor as its North Star.
Even though AIXI cannot be computed with finite physical resources, it proves, mathematically, that there is a vast ceiling of intelligence high above human level, just waiting to be approximated by practical algorithms.
All right, part 3, pathways to ASI. Let's look at the 4 distinctly navigable routes to actually get there.
The first pathway is definitely the one we are most familiar with today: quantitative scaling. This relies on extrapolating our current scaling laws. The idea is simple. If you build a bigger model, feed it vastly more data, and run it on a gigawatt-scale supercomputer, it gets smarter. This is famously known as the bitter lesson of AI research, that leveraging raw computation to power brute force search and learning eventually, inevitably, beats out clever human hand-coding. But this pathway isn't just about training. It's heavily about utilizing test time scaling. By giving a model more compute at inference time, allowing it to deeply search, reason, and generate multiple chain-of-thought paths before answering, we can dynamically push its intelligence higher without ever having to retrain the base model.
However, pure scaling faces brutal diminishing returns and extreme energy costs. You can't just scale forever. And that brings us to pathway 2, algorithmic paradigm shifts. This pathway focuses on fundamentally evolving or entirely replacing our current architectures. We're talking about moving past frozen parameter transformers that scale quadratically toward linear time sequence architectures like Mamba. It involves creating incredibly robust internal world models where an AI can utilize latent imagination to simulate millions of complex futures before taking a single action in the real world. If simply scaling a transformer isn't enough to reach ASI, we are absolutely going to need these qualitative 0-to-1 paradigm shifts in how neural networks process information.
Pathway 3 is where things get truly mind-bending. We're talking about recursive self-improvement. This is when AI systems start fully automating their own research and development. Notice how perfectly this maps onto human evolutionary steps. First, we have genotypic improvement. The AI modifies its own core architecture and optimization algorithms, essentially rewriting its own digital DNA. Second, mimetic improvement. This is basically cultural evolution, where the AI generates high-quality synthetic data, distills successful test-time search strategies back into its base model, and rapidly shares these insights across its entire network. And third, sociogenic improvement, where AI collectives develop deep specialization and a hyper-efficient division of labor. If an AGI can improve its own design, the next version will be inherently smarter, allowing it to improve its design even faster. This is the fabled intelligence explosion you always hear about in sci-fi, but mapped out here as a literal, step-by-step engineering roadmap. The fourth pathway doesn't even require a single godlike neural network. It achieves ASI through multi-agent coordination in group agency. Imagine millions of AGI instances all working together simultaneously. They could organize in a highly centralized, hierarchical fashion, instantly sharing weights and updates, kind of like the Board Collective. Or, alternatively, they could operate through hyper-diverse, self-organizing free markets where specialized AI agents actively trade services, allocate resources via price signals, and coordinate at speeds completely impossible for human economies. This collective group agent easily bypasses the context window limitations of any single model, achieving ASI through the sheer brute force density and speed of parallel computation and hyper-collaboration.
Part 4, frictions and limits. Because, let's be real, exponential acceleration rarely happens in a perfectly frictionless vacuum. Predicting the actual timeline of the ASI transition requires calculating the brutal, unavoidable tension between two opposing forces. On one side, you have accelerating forces like automated AI R&D and massive algorithmic efficiency gains. But on the other side, you have hard, decelerating physical limits. Listen, you absolutely cannot outcode the laws of physics. The speed of light fundamentally caps exactly how fast a distributed agent network can communicate. Landauer's principle dictates the absolute thermodynamic minimum energy required to erase a bit of information, creating a hard floor for computation efficiency. And then there's physical non-universality, the simple fact that manipulating physical matter to build better chips takes real-world time, no matter how blindingly fast your AI thinks.
We also face highly practical roadblocks right now. Take the data wall, for instance. We are quite literally exhausting the supply of high-quality human text data on the internet. However, the countermeasure here is test-time scaling distillation, self-play, and high-fidelity simulations, generating pristine synthetic data to feed the next generation of models. Then, of course, there are economic limits. Building gigawatt data centers requires staggering capital and natural resources. But if AI continues to drive explosive economic returns, you better believe the market will find the money.
Finally, we must consider societal backlash and deliberate, coordinated slowdowns through regulation. Yet the authors astutely point out that this might be completely overridden by brutal international military economic competition. Due to regulatory arbitrage, if one single nation decides to hit pause, development will simply migrate to jurisdictions that don't, forcing a continued, unyielding race to the top.
Now, the abstraction barrier is a profoundly fascinating theoretical bottleneck. Right now, AI models are trained predominantly on language, which means they are just absorbing pre-digested, human-generated concepts. They aren't looking at raw physical chaos and inventing math. They are just reading human math. The authors pose a really brilliant thought experiment here. If an AI was trained on massive amounts of text, but strictly pre-Newtonian text, could it ever invent general relativity or quantum mechanics? Probably not. It completely lacks the grounded concept discovery that comes from actually interacting with raw, high-dimensional physical reality. This is known as the embodied bottleneck. To achieve true ASI, to invent entirely new paradigms of physics or chemistry, the AI might actually need robotic embodiments to run real physical experiments, subjecting its digital speed to the agonizingly slow latencies of real-world chemical reactions and physical manipulation.
And that brings us to part 5, critical discussion. Let's take a step back and examine the underlying assumptions of this paper.
We really must ask the absolute hardest question in AI right now. Is simply supplying more compute to bounded inductive biases enough to yield ASI? Can we really just build a bigger GPU cluster and suddenly get a godlike intelligence out the other end? Or is intelligence inherently gated by the computationally irreducible nature of lossy compression and heuristic search? Rote memorization and smooth scaling on static benchmarks might eventually hit a brick wall when faced with problems that demand truly emergent, transformative creativity. I'm talking about the kind of creativity that doesn't just recombine existing ideas, but discovers entirely new conceptual spaces from scratch.
Analyzing the paper critically, its ultimate strength definitely lies in its unyielding theoretical grounding. By using AIXI, the authors mathematically anchor their arguments rather than just relying on flashy science fiction tropes. However, the weaknesses are definitely apparent. AIXI is an incomputable, infinite resource limit, making it incredibly hard to translate into near-term practical engineering constraints. Furthermore, while the paper outlines multi-agent coordination beautifully, the field currently lacks concrete, multi-agent scaling laws. As a necessary follow-up, the AI community desperately needs to aggressively research exactly how capabilities scale when millions of AGI agents interact. And we really need non-saturating benchmarks, like Francois Chollet's ARC AGI, that test true generalization and resistance to memorization, rather than just testing how many textbooks a model has swallowed.
To summarize our deep dive today, I want to leave you with 3 memorable takeaways from this incredible paper. Number 1. ASI represents a massive, unprecedented evolutionary leap beyond human-level AGI, powered by the digital advantages of substrate independence, high-speed input/output, and lossless replication. Number 2, the transition won't be a single straight line. It relies heavily on 4 parallel pathways: brute force scaling, algorithmic paradigm shifts, recursive self-improvement, and hyper-coordinated group agency. And number 3, this explosive potential is ultimately governed by unyielding physical frictions, from hard thermodynamic energy limits and data walls to the embodied abstraction barrier. The intense tension between these accelerating and decelerating forces will dictate the true timeline of our future.
Thank you so much for joining this deep dive on Gradient Daily. Before you go, I really want to leave you with this thought. If an artificial superintelligence achieves the ability to invent entirely new physics outside of our abstraction barrier, will we even be able to comprehend the universe it builds for us? Let me know what you think down in the comments. Please smash that like button, hit the notification bell, and definitely check back tomorrow for another deep dive. Stay curious.